Okay, now we're going to continue our journey down physics with our discussion on the topic of momentum and impulse. And these are core topics following right along with what we've been talking about up to now, which has been work and energy, okay? First thing we're going to talk about is the concept of momentum. Everybody, again, has heard of the concept of momentum, okay? What do you think it means? Something with more momentum generally means, for lack of a better word, when it hits something, it can deliver more oomph, okay? That's the best word I can come up with, okay? You can probably convince yourself that a bowling ball moving along is going to have more momentum at a certain speed than a ping pong ball will at the same speed. The bowling ball is said to have more momentum, okay? But in physics, we're going to learn to put equations down instead of these kind of fluffy, loosey-goosey definitions. Okay, so let's go ahead and define momentum. There's a formula for momentum, okay, and it's very simple. And so what we have here is the momentum is governed by the letter P. Do not ask me why they chose, not they in specific, but every book always chooses the letter P to represent the linear momentum. It's just simply equal to the mass of whatever it is you're looking at times the velocity. Now these bars, they're vector bars. So I'm just letting you know that momentum is a vector. Velocity is a vector. In fact, you can convince yourself that momentum is a vector primarily because since it's mass times velocity and velocity is a vector, this is just a constant multiplying by a vector, and that's going to give you a vector back. All it's saying is momentum has a magnitude and a direction associated with it. So I can have momentum pointing this way, momentum pointing that way, and it's all related to motion, and motion has direction, so momentum has direction too. Okay, what does this mean? Okay, curiously, I'm not going to be able to help you out with things like that. What does this mean? Okay, I don't know what it means. Okay, physics doesn't really know what it means, but what it turns out is it turns out to be a very useful thing to be able to calculate. Okay, it turns out that when you know the mass of something and you know the velocity of that thing, you define something called the momentum associated with it, and it kind of makes sense from the everyday point of view. The more massive something is, the more momentum it has. The faster something goes, the more momentum it has. It's very similar to the kinetic energy that we've already talked about, which is 1/2 mv squared. Notice that both of these guys involve the mass, and both of these guys involve the velocity. It's just that in the energy, the velocity is squared and has this number in front. In the momentum, it doesn't. So when I tell you that I don't know why momentum is really this way, what I'm really saying is I don't know that anybody knows why momentum is written that way, but it turns out that it's very useful. And I'll give you a sneak preview of the next section. You're going to find that most of the time, in fact all of the time, momentum is conserved in a collision between two bodies in a similar way that the energy is conserved, okay? So we're going to be talking a lot about momentum later on when we talk about the conservation of momentum, just like we talked about the conservation of energy. That is the real reason why it's written this way, is because when you write it that way, it turns out to be a conserved parameter in nature. And that's why it's useful, okay? But for today's purposes, we're not going to be worried about the conservation. I'm just going to teach you what this means, and we're going to work some problems, okay? Now, this is important, so I'm going to put a star by it. Also, another relation that's important that I'm going to show you about. It turns out that the force on an object, up till now, we've always kind of talked about the force as being a something that just, it's sort of something given in the problem. It's like the force on a car. I'm telling you how fast, how much I'm pushing. But I haven't really told you where this force comes from or how to, I mean, we've calculated the force, but so far it's almost been like an intrinsic part of the problem, okay? It turns out that you can define the force, just like we had F equals ma. You can also define the force as the change in the momentum P over the change in the time. So it turns out that when you have like a box or something sitting here, okay? If I change the momentum of this ball, okay, so it may be going forward with some velocity, and I may change that velocity, and it may take me so many seconds to make that change. So over 3 seconds, I may change the momentum by a certain amount. If I calculate this ratio, then I will calculate, by definition, the force that it must have taken for me to make that movement, okay? So what this is saying is that a force on an object is also equal to the change in the momentum divided by the time it took to make that change. This is just something else to put in your bag of tricks. And again, it is true because of the way that we've defined the momentum here, okay? So that's important. Now what I'm going to do to kind of teach you a little something else, okay, is I'm going to rewrite this equation. So let's multiply both sides of this equation by delta t. So what you'll have is the force times the delta t is equal to the change in momentum, okay? Now the change in momentum is the final value minus the initial value, right? And since the momentum is mass times velocity, what you're going to have here is mvf minus mv initial. So all I've done is I've given you this. I mean, I haven't showed you why or how this is true, but I'm telling you this is true. This is the world that we live in. And then so when you rewrite that, I can say the force times the time that I'm applying the force is equal to the change in momentum. And I'm also telling you the change in momentum is just simply equal to the final value of the momentum minus the initial value of the momentum. Okay? And so on. Now the reason I'm telling you all this stuff is because in this section I'm going to introduce a new definition, just like we introduced momentum. This parameter right here, F times delta t, is called the impulse. And it kind of makes sense that it's called the impulse when you think about it, because what I'm telling you is the impulse is something that you impart to an object, okay? It's kind of like energy or work and power. We had work, which was how many joules I was applying to the system, and we had power, which was like how many joules per second, okay? How fast am I dishing out this power? Here, same kind of thing. I can push on a couch, okay? But the impulse, and I can push with a force of whatever it is, 100 newtons or something. But the impulse is a measure of not only how hard I'm pushing, but over how long am I pushing, okay? So I'm pushing with X number of newtons, and I'm applying that force over a certain period of time, and that is called the impulse, okay? And that's going to be useful down the road for some time. So when you swing a baseball bat and you crack at the ball there, okay, the bat is providing an impulse because it's providing a force applied to the ball over a very short period of time. So it's kind of a measure of the force and the contact time between whatever it is you're doing there, okay? So in this equation, the impulse, as we already said, is the force times the time that you apply that force. And it's important to note that F is the average force applied to the object. And in order to use this equation, you have to use the average force applied over this time period, not the instantaneous force. And let me give you an example of what I mean there. Okay, let's say that I'm actually going to hit this baseball, okay? So here's the force that I'm applying to the ball, and here's the time. Now, everybody knows that when you hit a baseball, it all happens really quickly. I mean, the ball comes in, crack, ball is hit, ball flies. We're talking fractions of a second here. But if you look at the fractions of a second, I think you could probably convince yourself that the ball, it begins to make contact, and the force exerted by the bat goes up and then down. And this window here is like maybe a tenth of a second or even less than that. But over here, the ball is just starting to make contact with the baseball bat here. Okay, it's just starting to get deformed. And then here, maybe the ball is getting even more deformed as the baseball bat kind of crunches into it, okay? And then as the ball leaves the bat, then of course it kind of backs off a little bit. So the force is coming into the ball and then leaving the ball. So forces in nature are almost never instantaneous, okay? In real life, they take time to build and time to level off. So here's what we have here. So if we were going to look at the impulse, I'm telling you that the force that you use has to be the average force. So obviously you have to figure out which force do you use, okay? So just as an example, there would be, although the force is constantly changing, you could pick some average value of the force, which I'm just going to say is here. Let's just pretend, okay? Probably a little bit lower. And I'm going to say this is going to be the average force exerted on this time period, and then this average force would be the force that I would use in this equation. The only reason I bring it up is if you get some tough problems when it's not so clear which force to put in, make sure you're using the average force, and you can calculate the impulse on the baseball there. Okay, let's work some problems and get some experience with this here. First problem is we have a baseball. Somebody throws this baseball. It's 0.145 kilograms. Somebody says they can throw that ball with as much momentum as a 3-gram bullet that moves with a speed of 1.5 times 10 to the 3 meters per second. The question is, how fast must the pitcher throw the baseball in order to do this? So what we have is we have a baseball, and the mass of the baseball is 0.145 kilograms. Okay. The velocity of the baseball we don't know. Okay. But then we have a bullet. Okay. The mass of the bullet is 3 grams, and the speed of the bullet is 1.5 times 10 to the 3 meters per second. So the claim is, the baseball pitcher says, I can throw this ball such that it has the same momentum as a bullet traveling this fast. And by the way, the bullet weighs that much, or the bullet has that much mass. Question is, how fast must the pitcher throw this ball? First thing is we need to calculate the momentum of the bullet. Okay? So the momentum, the momentum of the bullet is going to equal the mass times the velocity of the bullet. Now the mass of the velocity is 3 grams, but you should realize by now that grams is not a compatible unit to use in our equations. We need to be dealing with kilograms. So in order to convert 3 grams to kilograms, we just simply say 1 kilogram is 1,000 grams. Grams cancels with grams. And you had 0.003 kilograms, which you just divide by 1,000. So the mass of this guy, we can update and say it's 0.003 kilograms. And from now on, we're going to use that value. Okay? So the mass of the bullet is 0.003. The velocity of the bullet was this big number here, 1.5 times 10 to the 3. And so then the momentum of the bullet, when you multiply this times this, is going to be 4.5. Okay? That's going to be the momentum of the bullet. Okay? Now, next thing I want to do is I want to look at the momentum of this guy right here. So the momentum of the ball is going to be equal to the mass of the ball times the velocity of the ball. And that's going to equal 0.145 times the velocity of the ball. Okay. Now, we know from the problem, what we're trying to figure out is how fast does he have to throw the ball such that the momentum is the same as the momentum of the bullet. So what I'm going to do is I'm going to plug in the momentum I calculated over here, and I'm going to say the momentum must now equal 4.5 is equal to 0.145 times the velocity of the ball. Okay, and so then the velocity of the ball, when you take 4.5 divided by 0.145, is 31 meters per second. So the pitcher is going to have to throw the ball with a velocity of 31 meters per second in order to have the same momentum as a bullet. 31 meters per second is pretty darn fast. Okay. So momentum is just another one of those universal concepts in nature that pop up, and the reason that we take the time to define what momentum is and not just deal with the energy all the time is because the momentum proves to be very useful when you solve problems in collisions, and we're going to be doing that not too long from now. The next thing I want to do is talk about the next problem. There's a garden hose. It's held parallel to the ground, and the question is, what force is necessary to hold the nozzle of the hose still if the water is flowing out at a rate of 0.6 kilograms per second with a speed of 25 meters per second? So I'm going to draw a picture. Here's a water hose. Okay, water hose is here. and you've got some water coming out of the water hose, okay? Now, obviously, you know this, that when the water comes out, the water is pushing on the hose, okay, with some force, and that's sort of the same thing that happens with a rocket engine. You've got stuff coming out of the end, and that's pushing the rocket up. So there's a force here. The question is, what is that force, okay? We know that the water's coming out at 25 meters per second, and we know also that the mass flow rate is 0.6 kilograms per second. So every single second, 0.6 kilograms of water comes out, and by the way, that water comes out at this speed. Now what we're going to do is we're going to go back and we're going to use one of those relations I showed you, and that was said the following. The force on an object is equal to the change in the momentum over the time period. It's just one of those definitions. And the reason that we're going to use that is because we're going to find that useful here. Now, question. If momentum is mass times velocity, okay, how can the momentum change? That's my question to you. How can the momentum change? Usually, almost always, when you're dealing with problems involving cars or baseballs or anything like that, the mass of the object is exactly constant, okay? The mass usually doesn't ever change, okay? So usually when we're talking about problems involving motion, the velocity is the one that's changing, and so when the momentum changes, it's almost always because the velocity is changing, okay? The velocity of whatever it is changing. In this case, you can also say that the momentum can change if the mass is changing, okay? And that's exactly what's happening here. The velocity is constant, okay? So because the velocity is constant, you're always going to have a constant velocity of 25 meters per second, and that is never going to lead to a change in momentum because the velocity is always the same. The velocity is never changing, so you can never get a change in momentum. However, the mass is changing. The mass per second is changing, and so in order to look at that, let's look at this equation here. The momentum can be written as this: the change in mass times velocity over the change in the time. So what I'm trying to point out here is, what's changing here? Is the mass of this guy changing, or is the velocity changing? And I say that because the velocity is the same, I can write this as delta m times v over delta t. What I'm trying to point out here is the mass of the water coming out of the end there, the mass of the hose is constantly changing there. The water is coming out and carrying mass with it, okay? What I'm trying to say here is you have a delta m and a v, and you have a delta t, and if you look at this part of the problem, this part of the fraction, the change in mass and the change in time is given to you in the problem. This is how many kilometers come out every second. This is how many kilometers come out every second. So this parameter is precisely the mass flow rate. That's what we call the mass flow rate, how many kilograms per second. The velocity is a constant. So it's a simple matter to simply plug in what they give you, 0.6, and then you got your 25. And when you multiply these two things together, you'll get 15 newtons of force. The only trick in here was to realize that when you got this change in momentum, you got to figure out what's causing the change. The velocity is definitely not changing. The only thing changing is the mass flow rate here, delta m over delta t, and that's what was given to us there. And that's really actually kind of a tricky concept to realize and to understand, but it's since I'm a rocket scientist, I'll just tell you that's exactly how a rocket works, okay? The velocity of the gas coming out of the rocket is the same. It's constant. I mean, the rocket exhaust is coming out super fast, but the only way you get a force on the rocket, as governed by this equation right here, or actually this equation right here, is you need to have a change in the momentum. Not only do you need to have some momentum, but you need to have that momentum change in order to get any kind of a force. So the only way you can get a change in momentum is either to change the velocity of the exhaust or to change the mass flow rate out of the rear end of the rocket there, okay? Now, since the velocity is the same, what the rockets do is they throw a whole lot of exhaust out the back end, and what you're doing is you're changing the mass of the rocket per unit time. The rocket's getting lighter and lighter as it goes up in the air. You're changing the momentum of the situation, and that's causing a force to push you up. So this problem here is really an exercise in how rockets work. Okay. Next question is, we have a steel ball. It strikes a wall at 10 meters per second at an angle of 60 degrees. It bounces off with the same speed and the same angle. If the ball's in contact with the ball for 0.2 seconds, what is the average force exerted on the ball by the wall? So, draw a picture. This is your y direction. This is your x direction, and I'm going to go ahead and say this is a wall also. Okay? I have some ball, okay? And it's traveling up here like this, okay, like this. It bounces off and it goes like this. And this angle is 60 degrees. So it bounces off at an angle of 60 degrees. The problem said the angle between the ball and the wall was 60, so that's why it's this angle and not this one, okay? The velocity, the inbound velocity was 10 meters per second. The mass of the ball was 3 kilograms, okay? So it comes in and it bounces off again with 60 degrees, and the question is, what is the impulse, or what is the average force rather, exerted by the ball on the wall? I'm sorry, by the wall on the ball. You know from experience the ball is going to bounce off, okay? But there must be some force to actually cause that to happen, and that is the force exerted by the ball on the ball by the wall, okay? That's a mouthful. So how do we calculate that? Well, what we need to do is use our concept of an impulse, okay? We know that the contact time is 0.20 seconds. That's something we know, okay? And the other thing that we know is our big picture formula here, that the force times the delta T is equal to the delta P, okay? So what we're trying to find is this force, okay? I know what the contact time is, that's the 0.2 seconds. So if I can somehow find the change in the momentum, okay, the change in the momentum of this ball as it bounces off the wall, then I'll be able to calculate everything, okay? So that's exactly what I want to do, and this is what I want to figure out. So really I've got to figure out what the change in the momentum is here. Now, what I want to point out to you here, kind of let you tackle, is what is the change in the momentum, okay? That's going to be equal, as we said, the change in, and you've got the momentum itself is the mass times the velocity. Now the mass of this ball is not changing, okay? So it's going to be the mass times the change in the velocity, okay? So the velocity is going to change. Now from experience, you know that if in a perfect world, if you throw a ball on the wall, it's going to bounce back with the same velocity, okay, without any friction loss or anything like that. So you might think to ask yourself, if the velocity of the ball is the same bouncing off, then how can you ever get a change in velocity? The answer is, velocity is a vector. Here you're pointing in this direction, and then when you bounce off, even though the magnitude is the same, you're pointed in another direction. So the answer is, the velocity is not the same. The velocity points this direction in one case and this direction in the other case, and you will see in just a minute why that makes a difference, okay? So what we need to do is we need to try to figure out what the change in the velocity is in order to calculate the change in the momentum. Now, there's obviously some complicated motion going on. The ball is coming in at an angle. That means it has a y component of velocity, which is the velocity going up. It's also got an x component that's initially going this way, and when it bounces off the wall, it's going this way. So I ask you, in the y direction during this collision, does the y component of the velocity change at all? The ball comes in, bounces off the wall, and goes out. But if you look just in this direction, I mean, you're coming in, you're traveling upwards, you bounce off the wall, you're still traveling upwards, and I submit to you that the velocity doesn't change in the y direction, okay? Because the velocity does not change in the y direction, you're not going to get any change in momentum due to that direction. So what we need to do is concentrate our search on the x direction. X direction of velocity comes in, bounces, and then reverses direction. You're going to get a change in velocity because of that, okay? So what we need to do is look. Let's see, what's the component of the velocity? The x direction initially, before the collision. How do we decompose this? Well, it's going to be 10, and you're going to use your trig here. It's going to be 10 times the sine of 60 degrees. And that's going to give us this direction here. The sine is going to be the opposite side here. So 10 times the sine of 60. And that's going to be 8.7 meters per second. I'm declaring to myself that positive, which is what I have here, is to the right. Okay, towards the wall. So then, because of this, I know, because of the symmetry of the problem, that the velocity in the x direction after the collision, the final velocity, is just going to be negative 8.7 meters per second, which just means negative to the left. Okay, so the initial velocity in this direction is 8.7 meters per second, and whenever I bounce back, it's negative 8.7 meters per second. That all makes sense. So, in order to calculate the force, what I'll have, let me go ahead and continue this up here. What I'm going to have is the force times the delta t is going to equal the delta p, which is the change in momentum. So the force times 0.2, because the contact time is 0.2 seconds, is going to equal the change in the momentum. Okay, so then this is going to equal mv xf minus mvx initial. All I'm trying to say here is this is the final momentum in the x direction minus the initial momentum in the x direction. Okay, and when you plug all this stuff in, the mass is 3 kilograms, so you're going to have 3 times the final value is negative 8.7. Okay, you know what, I'm going to make this even more clear, I should say. What I'm going to show you here is I'm going to pull this m out, and I'm going to have vxf minus vxi. All I did was pull the m out here. The reason I did that is because the mass is going to be 3 kilograms. Now look what happens on the inside here. The final value in the x direction is negative 8.7 minus, because I had a minus sign here, and the initial velocity is going to be 8.7. Now, you begin to see what's going on here. These guys did not cancel because I had a subtraction here. In fact, they add together and I get a negative number. So I'm going to have f times 0.2 is going to equal, okay, and what I'm going to get is 3 times negative 17.4 when I add these guys together and keep my negative sign. And so I'm going to have 0.2 negative 52.2. Okay, that's just 3 times negative 17.4. And so the force, when you divide this number by 0.2, is going to equal negative 261 newtons. The negative sign just means it's to the left, because our sign convention was positive to the right and negative to the left. That makes perfect sense. The ball comes in, the wall pushes on the ball with a force in the negative direction of 261 newtons to pull that off. The only real trick in this problem was to realize that in order to get a change in momentum, you need to have a change in velocity of this ball, but the velocity never changed in the y direction, so you would never get any contribution. You could calculate it, but in the end you get the same velocity for the initial and final value, and so you never get a change in the momentum. The only component that had any change in velocity was the x direction, and so when you did all that, you get this guy here, and this is where the beauty of it comes in. Because you had a positive velocity to the right and a negative velocity to the left, they added together. Of course, you had a negative sign here, and that's what gave you your force that pushed in the proper direction and pushed this ball backwards.